This is Manning Publications. My name is Jeff Fritz, and today we're going to talk a little bit about how we model language as tensors. And I've got two guests here joining me today. This is Chris Mattmann over here on my upper left, and over here is Dr. Scott Penberthy. Let me introduce them. They've been working on a couple of books. They've been working on a couple of blog posts all around the idea of TensorFlow and making reading and comprehending language a little bit easier. You're going to see a link pop up here in the chat every couple minutes that links to a Medium article called The Ultimate Speed Reader, talking about using TensorFlow and a tool called BERT. We're going to learn more about both of those in a few minutes. Let me introduce first Chris. Chris Mattmann is the Deputy Chief Technology and Innovation Officer at NASA's Jet Propulsion Lab, where he's been recognized as JPL's first principal scientist in the area of data science. Chris has applied TensorFlow to challenges he's faced at NASA, including building an implementation of Google's show and tell algorithm for image captioning using TensorFlow. He contributes to open source as a former director at the Apache Software Foundation and teaches graduate courses at USC in content detection and analysis and in search engines and information retrieval. Good to see you, Chris. Hello.
Thanks for having me on the program, Jeff.
And over here is Dr. Scott Penberthy. Now, he's a director of applied AI at Google. Dr. Scott helps train people on how tensors work, how they flow through computational graphs, and how to use powerful new cloud-based IDEs. Tensors are the heart of Google, enabling us to reason with images, video, text, and speech. What the industry calls unstructured data. Yes, I TensorFlow. Good to see you, Dr. Scott. How's it going?
Hey, morning or afternoon, Jeff. Good to see you too.
Oh man, when I read through and I was learning more about BERT and TensorFlow, and I was really getting into this, the article hits a problem, hits a thing that I think a bunch of us have here, right? And it's talking about, the article talks about speed reading, analyzing data, and in a time of COVID, in a time when so many folks are, and I'm going to share a link to that article in chat, so many folks have so much data being thrown at them, right? And I look at my phone right now and gosh, I've got 48,000 unread messages. Let's get into this simple and start simple. What are tensors, and how do we use them to analyze text?
Maybe I'll take a stab at that one, Jeff. I think tensors actually came from at the dawn of time. Almost seems like the dawn of time, around the time of Einstein. He wanted to figure out how do you represent time and space in the same sort of calculus, and he used something called tensor calculus. Like what is that? And what it boils down to, if you take away some of the physics implementation of it, it's sort of just a multidimensional vector. And I'll give an example. So a 0D tensor is like a cell on an Excel spreadsheet. 1D is sort of a column. A 2D is a sheet. A 3D are a bunch of sheets. 4D, a bunch of computers. And so you can just take these ad nauseum, and what happened is it's a well-formed multidimensional vector in the sense that all the rows and columns go all the way to the edge, and it's like these cubes in a very high space. And a lot of tensors we'll talk about, they have some interesting properties. One, you'll see that a lot of these algorithms we use, the values in those cells, they tend to be between -1 and 1 because these graphs are very, very sensitive, extremely sensitive to the way they work. And what you end up doing is, a tensor is a way to encode all kinds of things that we see. We can get into more details. Anything else that you might want to add on that in terms of tensors flowing through graphs, Chris?
Yeah, my big thing, is that it really started to make sense to me when I thought of it as sort of an activation map. So, we do a lot in climate science with masking out information. Just work with a lot of climate people at JPL, and what a mask is just a sheet that information passes through. And like Scott was saying about tensors, it's that just imagine them as different dimensional sheets that have some sort of filter on it. And we're really concerned about that, when we talk about information in areas, say geographically, that matter to us. You can think of a tensor as just that sheet that information passes through, just some mask that sort of identifies and represents that information and how you manipulate it. But I don't have anything else to add. You nailed it, buddy.
Yes. I think what's interesting here, Jeff, is that tensors to me, my license plates are Tensor 1, Tensor 2. So, I'm a big fan. I think that, to me, it's a new style of representing features and data structures in computing. The number of people who know this, there's 10,000 who think about this every day, and the programmers at TensorFlow and PyTorch, they don't give it second thought. The rest of us probably never heard of it before. And I think, it's like as common in AI as a relation is in the database world, or like a JSON structure is in something else. And so I think as more and more learn about tensors, like we use them at Google for representing language, for representing speech, for representing us, for URLs, it's a very compact way to represent a lot of information and reason about it.
So tensor is that base unit of storage and manipulation for machine data that we're talking about. In the article, it talks about the tool BERT, right? And there's comically a picture of the Sesame Street character BERT. What does BERT do when it gets these tensors?
So we have 2 hours for this? Is that what we're going to talk about?
Well,
I don't know. I'll take a whack at it, Chris. I don't know. So BERT, I keep thinking that they probably just like Sesame Street characters and had to reverse engineer the name. That's what we all do, right? I want to name my program this, and the name I think stands for, bidirectional encoding representations using transformers, where it comes from. And what's neat about BERT, and we can get more detail if you'd like, is that you can represent words as a tensor.
Okay.
We can get to how you do that. And what's neat about BERT is you can also represent paragraphs as tensors. And what the way that all these algorithms work is that you take a tensor, and you mentioned it, Chris, right? You take a tensor and you flow it through what do you call a sensor? You call it a map, right? An activation map. What happens is as you flow tensors through a graph, you can change them a little bit. And a lot of the AI systems are tensor in, tensor out. That's how it works. And what BERT is that it's sort of an ingenious idea. They said, what if we built an AI and fed it the internet? And, like all of it. So I guess you think that way, Google, I guess. And so what they did is they said, here's how the setup. We're gonna take a chunk of text, paragraph, and we're gonna code that as a tensor, and that's your input. What we're gonna do is we're gonna play Mad Libs. We'll take a chunk of text, and we're gonna block out 5 words, let's say. And then we're going to flow it through a graph, and the graph has got to guess what 5 words are missing. And you can imagine if you have Wikipedia and you chunk it into paragraphs, you've got a very, very large set of paragraphs, and you can just pick out 5 words. And you can be a little smarter about it and pick out words that are meaningful, not just the and, but pick out words that are less common. And if you train an AI, which BERT did, at the time it was the best in class. And something just trumped it, I think, last week. I think it's called Marge. But BERT, the idea is that if you train an AI, what ends up happening is the AI, it starts to figure out how the words mean in the context of the paragraph. Because so what's happening is you're feeding BERT a paragraph in, and it's got to guess 5 words. After a few million of these, it starts to get the hang of it and know in these blanks, these are the kind of words I want to see appear. And those representations of those words have a lot of contextual meaning that is more like, for example, the word bank. Bank, for some of you thought, oh, that's where I put my cash. If for those sports car fans, they said, no, I'm thinking about banking around a corner. If you're a canoe fan, you're like, no, I meant riverbank where I put my canoe. And you're all right. And the point is the word bank has context. And this is one of the first breakthroughs where the computer can now represent a tensor that has that context. And that came from sort of 2018 it came from a team of Googlers. And now it's sort of an interesting technique that sort of has taken the world by storm. And using that stuff in representing language is now, there's all kinds of derivatives, and they're all trying to one up each other. But what's interesting about it is that we now have a representation for language that's starting to mimic how we think about words. I don't know. What do you think, Chris?
For me, it feels like every couple years, like Scott was saying, like there's one of these sort of transformative, applications of machine learning, and especially, deep neural networks, and especially using frameworks like TensorFlow and so forth, with lots of smart people in Silicon Valley. And the early attention, I think, was paid, say, in the mid 2010s to, images, video and things like that, because I think those were at least the place that were kind of at the tipping point where they felt like we could move the needle ever so slightly, and it was right there. And it feels like over the last 5 years, they've turned around on some of those approaches, and not just use them for things like prediction, and things like that, but to come up with representation and to apply it to things like text. So I mean, I come from a lot of statistics background, and so forth, where it's like you see across all of the domains, people are saying, oh God, what are these black boxes? What are these neural networks doing next, to kind of invalidate all my statistical assumptions. And it keeps getting kind of turned on, the latest, people in the blog sphere and Twitter that were, killing each other or getting pissed off were, say the people dealing with machine translation, because all of the approaches to that, from translating from one language to another, which is a big text, sort of problem related to deep learning. All of the approaches for that were really based on language. They were based on knowing a lot of statistics about word properties and things like that that weren't put together in sort of a way that was like we think, like Scott's talking about, biologically inspired. And the beauty of all of these, techniques, that the things like BERT, are that all we do is we look at biology. We look at the way, just like with computer vision, and we look at the way the brain activates, when we see certain images, what types of labels that, fires off in our mind and things like that. This is the same concept kind of applied to text. It's like Scott said, it's, putting together patterns in our mind of Mad Libs of words and sentences that we want to complete, and then trying to fill them in with what fires or what activates when we see things. And if you feed it the knowledge of the history of the world, which, you or I, or, Jeff, Scott, I don't know how much time we have, like Scott said, but that would take us quite a while. It doesn't take the computer quite a while. You get those feature representations after that, and you can play ball, so I'm tracking.
It's interesting because I think some of us have seen there's some very well documented and shown sentiment analysis demos where, right, people run sentiment analysis against Twitter, and you could see when people are getting angry as something's happening, or, right, the Super Bowl, you can see, right, here in the States, right, American football championship game, and all the people in New England are happy that the Patriots are winning, and people in the rest of the country are not, because nobody likes New England. But, right, I feel like sentiment analysis.
Brady's in Florida now, there, so.
Yeah.
Well, we'll see what happens. But I feel like sentiment analysis was, from hearing you, Chris, I feel like sentiment analysis was almost like a gateway drug, where, right, we got that initial concept of the machine knows what some of these words mean, the feelings and the emotion when they're being pulled together there. Are you telling us that BERT knows even more than just sentiment of things and can relate things together?
Absolutely. That's one of sort of the natural kind of enclaves that BERT fills a gap in. And I know quite a bit about sentiment analysis or whatever, and the earlier models basically to do things like that all relied on this sort of concept called bag of words, which is coming up with a representation that sort of made sense to us. I think if you were looking at text, it's a big histogram of word counts and things like that. So words that occur more frequently, this is back 10 years ago, so it's naturally ancient. But, the old approaches for that were words that occurred more frequently in that histogram were more important towards the eventual label that you got for sentiment, whether it's positive, negative, or whether you slice that spectrum up into like, love, angry, mad, sad, like social media companies do. So you take a bunch of those features like you normally do in machine learning, which in those cases were counts from histograms, and then you try and see which counts or which most frequently occurring words imply that sentiment. That was sort of the naive approach. Wasn't biologically inspired, but it had that kind of concept about activations and things being more important. Here in BERT, it takes it to the next level. It's not just looking at word counts, which are sort of, I would say, shallow features. It's actually, taking a look at representation, relationship between words, co-occurrence, where they occur, sort of locality, and Scott, I don't want to embarrass him, the father of BERT, here, but I mean, it's like bag of words on steroids,
Yeah, well said, Chris. I think, bag of words is one way where you have human engineered features, right? And what we're finding now is that you can sort of stretch that idea and saying instead of a histogram of a few counts, you have sort of a very, in Bert's case, 768 values in the small case, right? So imagine, representing a concept as 768 numbers. And in there is not only sentiment, but things like the sense of meaning. And if you can imagine a very high dimensional space, what's neat about it is that those 768 values are just a point in space, right? Much like how you might, if you look at the brain, if I mention different political figures, turns out it activates the same part of your brain. And so what that means is there's different points in space are kind of close together. And so what's neat about BERT is that you can actually train BERT and continue to train it further, where such that you start to have these properties where points that are close mean the same thing. And that is sort of fascinating. So not only is sentiment in there, a lot more value is as well. And what's nice about this is that instead of having humans generate the features, which are still very powerful, word frequencies, statistics, that sort of thing, BERT gives you a very high dimensional, very fine-grained tool to represent the essence of the word. And then you can use traditional techniques to analyze those things. So we're basically looking at where do the points cluster? It's good old-fashioned machine learning. Or how often does this point occur? Things like it in this space. It's just a new machine-generated tensor as a new type of feature for how you represent words. It's super powerful.